Hello everyone. We are going to continue our discussion on secondary and electrons and backscattered electrons, right? So just a quick recap. The secondary electrons are electrons that are with energies less than 50 electron volts versus the backscattered electrons that are much higher energy electrons generated from the sample, right? So with this in mind, we figured out in the last class that you can use the Eberhard-Thornley detector for the detection of both secondary electrons and backscattered electrons. However, this detector is used more for the detection of secondary electrons, right? So you have the electrons that are generated, the low energy electrons generated from the sample that go through the Faraday cage, the scintillator, the light guide to the photocathode, and then through the photomultiplier or electron multiplier. There are the diodes that amplify it over 10 to the 5 or 10 to the 8 times. And finally, the electric signal is fed into the computer electronics, and you generate an image out of it, right? Okay, so the secondary electrons are generated from inelastic scattering. I hope by now I have said this enough times and it is etched and embedded in your memory. And just like the backscattered electrons, you can characterize the yield of the secondary electrons, where delta is the yield and NSE is the number of secondary electrons generated, and NB is the number of electrons from the incident beam, right? And we deal with current, so you can convert this number of electrons to the equivalent current, and that is the yield of the secondary electrons. Yes, and because these secondary electrons are generated from inelastic scattering, and inelastic scattering is promoted at lower energies, turns out that at lower incident beam energies, the yield of the secondary electrons is higher versus at higher energies, where the scattering by elastic mechanism is more prevalent. Okay, so now we know that the backscattered electrons are ones that travel at high velocity. They hit they approach the nucleus, and then they are deflected from the force field without the loss of any energy or momentum. There's just a change in the angle of the electrons, right? And this can happen over a significantly large volume of the interaction volume, right? So if you remember the image that I showed about 2 or 3 classes ago of the depth profile of the various processes in the interaction volume, you will find that the backscattered electrons probably penetrate somewhere between a few hundred nanometers to a couple of microns. Now we want to understand the same thing, but with the perspective of the secondary electrons, which are with low kinetic energy, right? So if something has low kinetic energy, you can intuitively say that the escape depth or the range for these low kinetic energy electrons are going to be significantly lower than the higher energy backscattered electrons, right? So I just want to clarify at this point that secondary electrons are generated in the entire volume of the interaction volume, the entire space, but only the fraction of secondary electrons that are generated on the very surface or close to the surface are the ones that make their way out. And this can be understood by looking at this relationship right here, which is the probability of the escape, and it is an exponential term where you have lambda, which is the scattering, which is the mean free path between two scattering events, and z is the depth below the surface, right? And we saw this relationship earlier in the course, where you can correlate the mean free path to the scattering cross section. So if you have a larger scattering cross section, that means you have a shorter mean free path, which means high Z metals or elements are going to have shorter mean free path, right? So you can plot this this relationship here, and you can see as you go from 0, which is the surface of the specimen, to about 7.5 nanometers, the probability decreases pretty significantly, all the way from 1 to close to 0. So you can safely say that any secondary electron generated 7.5 nanometers below the surface of the specimen is not going to make its way out. So you're not going to detect it with your Everhard-Thornley detector, or no matter how sensitive the detector is. It's simply because it's not making its way out. Okay. So let's take a look at what's going on. I briefly spoke about this in the previous video lecture, but I'm going to talk a little bit more about it so that you understand from the schematics what's really going on. So you have the incident beam, and the incident beam itself generates the secondary electrons, right? So there is an initial surge in the secondary electron generation from the incident beam, which is termed as SE1. And this incident beam then further travels down into the interaction volume. It undergoes several elastic or inelastic scattering. If it is elastic, it makes its way all the way up and it's gone. But if it is inelastic, it undergoes multiple scattering processes that is determined by the mean free path and also by the, if you remember the Betz equation, which is the energy lost per unit translation within the interaction volume. So all that comes into play here, and eventually some of them make their way out, right? And before they make their way out, these backscattered electrons, um, on their exit, they further ionize or undergo inelastic scattering somewhere here closer to the surface. That is the source of this generation of another bunch of secondary electrons, which are termed as Se2, right? So it was seen from the 1967 study by Seiler that the mean free path for metals is about 1 nanometer versus that of insulators, which is about 10 nanometer. And you can understand this from the simple description of transport of electrons in metals, where you have you associate a sea of electrons. In metals, those are the conduction electrons that are free to move around. So you have more scattering events in a metal versus an insulator, which is why the mean free path in a metal is relatively shorter than that of an insulator, right? And it was found that the maximum depth of emission is about 5 lambda. So if you correlate that to the relationship here, in case of a metal, if you have lambda equal to 1, and this lambda is not the wavelength of the electron, this is the distance of the mean free path. So about 5 nanometers means this is 5 lambda, right? So that means that is the 5 lambda that is shown here schematically. So you are basically collecting and detecting the electrons only generated within a depth of 5 lambda in case of the metal, which is about 5 nanometers. But if it is an insulator, this can be as large as 50 nanometers. Okay, and just by looking at the low energies of the secondary electrons, you can compare the escape depth of secondary electrons versus backscattered electrons, which is 1 over 100, right? So if this is 5 nanometers, that means you're able to, in case of secondary electrons, that means the backscattered electrons is 5 nanometers times 100, that's about 500 nanometers, right? So a backscattered electron can make its way out 500 nanometers below the surface of the specimen, but the secondary electron can't, right? So now you know that there are at least two kinds of secondary electrons. There are more, the secondary electron 3 and secondary electron 4. Those are generated due to inelastic scattering events occurring between the backscattered electrons that have made their way out of the specimen, along with the pole pieces and the other components in the electron column. I spoke about that in the previous video lectures, so please do. I want you to correlate that with this, because it seems like by fragmenting the lectures sometimes there's a loss of continuity. But either way, we are going to focus on Se1 and Se2. These are the ones that are generated from the incident beam and the backscattered electrons on the while they were going out of the specimen. And you can essentially, in a very simplistic form, write the total secondary electron emission or the coefficient as a sum of the secondary electron coefficient from Se1 plus the secondary electron coefficient from Se2 times the yield of the backscattered electrons, right? Because the number this yield delta 2 from the secondary electron 2 is directly correlated to the yield of the backscattered electrons itself, right? So if you have more backscattered electrons, then you have higher yield of Se2. If you have low backscattered electrons, you have lower yield of Se2. And again, this is related to the scattering cross-section, incident energy of the beams, and everything we have discussed in the last 2 or 3 lectures, right? So one way to identify and eliminate one from the other, right, is to use a very clever experiment that was done by Seiler in 1967, where he used thin foils, and these foils are thin enough that they are thinner than the 5 lambda depth itself. So if you have a foil which is 5 nanometers thick, that means the incident beams come right through, they do their scattering electron process, and then they just keep going because there is no possibility of them undergoing further scattering events and then eventually making their way out. So if you use a thin foil, you're pretty much blocking away the generation of secondary electron 2, because the backscattered electrons just look at the specimen as if it isn't there, and they just go past it, and then they continue on their way into the electron column, and they're corrected by the ground plates, and etc., etc. But essentially you get the idea that if you use a very thin sample which is thinner than 5 lambda, you can cut out the generation of Se2, right? So they did that kind of experiment, and they were able to block away the generation of Se2, so this component is completely gone, and then they see the contrast from the Eberhard-Thonley detector, and then you repeat the same experiment, but this time in the bulk form of the material. So for example, you take carbon, aluminum, copper, or gold, then you can find the total yield, and then you can find the ratio of the two electrons, two different kind of secondary electrons, and then you get an idea of what is the relative contribution of each of them in the while you're detecting it using the Eberhard-Thonley detector. Okay. So to summarize, we have seen that backscattered electrons are scattering is a scattering event, elastic scattering event. Second generation of secondary electrons is an inelastic scattering event, and they have their respective detectors that work great for the detection. In case of BSE, it is solid state detectors that rely on the p-n junction formation between two p and n type materials. They are usually electrons in the order of few kiloelectron volts. The image that they produce is called the Z contrast, or the composition contrast image, and then they are generated at different depths up to I'm sorry, there's a typo here. This is hundreds of nanometer or a few microns, right? And then the secondary electrons are for topography, right? And that makes sense. If you look at this image here, all the secondary electrons that you're generating or you're collecting and detecting, if it is only between 5 lambda, which is 5 nanometers in case of metals, that means you are essentially getting all the information from the topography alone. You're getting no information from the depth of the material. All the information you're getting is from the surface, and the surface is the topography, right? So the scattering electron, the secondary electrons from the inelastic scattering events give you topography images, which gives you the 3D view where you get an idea of the depth. It is a perception that you can visualize it. You can get an idea of the depth, but in case of backscattered electrons, you don't. In case of backscattered electrons, what you do get is a contrast between two different metals that tells you that one metal is or the two materials have different Z numbers, right? And then we just talked about it. The escape depth in case of secondary electrons is about 5 nanometers in metals and about 50 nanometers for insulators. Okay, so now we are going to move from this and understand a little bit more about secondary electrons and how they are involved in the generation of X-rays. So you have seen this image before in one of the slides in the previous lecture. You have the incident beam, that's your interaction volume, and depending on the depth from the surface, you have different processes. So you have secondary electrons that are generated and collected about few tens of nanometer from the surface. You have the backscattered electrons that can travel all the way, or that can be collected from about a micron depth from the surface. And then you have the characteristic X-rays and the Bremsstrahlung X-rays, and then you have XRF, which is X-ray fluorescence, which are processes that occur at larger depths in the sample. Okay, so the Bremsstrahlung, just to recap, are continuous X-rays that are generated. These are non-specific and they generally form a background in the energy. We are going to delve into this in more details. And then you have the inner shell ionization process that occurs, which leads to the formation of characteristic X-rays. This is important to do the composition analysis of the elemental analysis of the material that you're investigating. And just to emphasize, X-rays are also part of the electromagnetic spectrum, so you can associate a de Broglie wavelength with the X-ray, and then you have these X-ray detectors that essentially quantify the energy associated with the X-ray, and then you get more idea of what is there in your specimen, right? So this is the end game. I want to start with that. I want to show you what X-rays are capable of, and then keeping this in mind, we will look into the different processes that are associated in generating something like this. So what you're looking at here is an energy dispersive X-ray spectroscopy image generated for common salt. And this is something that is a consequence of a combination of characteristic X-rays, that is the inner shell ionization, and the Bremsstrahlung X-rays as well. So this is the SEM image of your common salt. This is what you put in your food, and then you can see that you have these characteristic peaks of sodium and chloride that is evident, and it gives you a good understanding of what your material or specimen is made of. And not only that, this is just an average collection of the sodium versus chloride in this entire space that is marked by the magenta box. But you can also create elemental maps. So essentially you can generate a map which will tell you whether you have a higher concentration of chloride here versus here, or if there is any impurity that you don't want in your table salt. So that's the kind of information you can generate from energy dispersive X-ray spectroscopy. Okay, so we will get into that in the next class. So what is inner shell ionization? Just a brief idea. Let's look at the schematic over here. So you have an incident electron. This is the electron that's coming from your beam, and it knocks off an electron from one of the inner shells. Right, so this electron flies on its way out. This is an inelastic scattering process, and this electron can make its way out if it is within the 5 lambda, right, where lambda is your mean free path. And then you have the scattering, this electron, the incident electron that's scattering into a different direction, and then this can lead to further processes down the line. Anyway, so let's take a look at this atom here. So now this atom is ionized, because there is an imbalance in the charge and it would want to go back to its ground state. So typically it takes about 1 picosecond for this atom to go down to its ground state. There are two things that can happen. One is that an electron from the outer shell, it moves into the inner shell because the electrons in the inner shell are at higher energy. So in order to thermalize or go back to its ground state, it will want to minimize the energy. So the electron from the outer shell goes back into the inner shell, and then there is a quantized energy difference between the two shells, and that quantized energy difference is emitted in the form of an X-ray, which is the characteristic X-ray, right? So that there you have your X-ray photon that is emitted. That is one process. The other is you have this thing occurs. So you have this electron from the outer shell that goes into the inner shell, and again it generates the X-rays, but the X-ray that is generated, or the energy associated with it, is sufficient to knock off another electron from the outer shell. as a result of which now you have an electron that is knocked off from the outer shell and it's on its way out, and those are called Auger electrons, right? So just want to emphasize, X-ray is a photon, whereas Auger process involves the knocking out of an electron, a physical electron from the atom itself. So the atom is back into its ionized state, but this is a different form of ionization here versus the ionization here, where an inner shell electron was knocked off. Right? So we will get into the mathematics of it. There are certain processes, there are certain allowed transitions, and then there are transitions that are not allowed. So we will look into all of that. We will delve a bit into the atomic physics, because I think that's important that you understand it. And then I will meet you in the next class, and we'll go from there. Okay, bye.